Hi everybody, Dr. Ahles here. In this short video, we're going to talk about the kind of macromolecule known as lipids. Lipids are my second major organic compound in the human body. Lipids have a very similar chemical structure to carbohydrates in that they have carbon, hydrogen, and oxygen. But compared to carbohydrates, they don't have nearly as much oxygen in them. So the same kinds of chemicals to build them, but at different ratios. When we talk about organic compounds, remember that we had this word polymer and this word monomer. So the polymer is the big version. When I use this word lipids in general, that's my polymer. What build these lipids are things called fatty acids. So little pieces, fatty acids, come together to build these large things called lipids. When we talk about lipids, we're going to bring back a word from a couple videos before, hydrophobic. Remember that hydrophobic literally means water fearing. So if something like a lipid is hydrophobic, that means that it does not play nice or it doesn't get along with water. That being said, something that's hydrophobic does get along with or does play nice with other lipids or with things called alcohols. So when we're thinking about terms that mean the same thing as hydrophobic, afraid of water, sometimes you'll see the word lipid soluble. Lipid soluble means that I play nice with other lipids, but I'm not going to play nice with water. There are three main kinds of lipids that we're going to explore. So the first kind of lipid is what we call a triglyceride. When we talk about triglycerides, these are the long-term energy storage in the body. Remember that carbohydrates were my accessible form of stored energy in the body. So this form, not nearly as accessible, but that being said, it's a lot more effective. We can store a lot more energy in it. And in addition to storing that energy, lipids also help to insulate the body to make sure that the body is warm enough in the cold weather. They also help to protect the body from trauma. That's physical injury. So for example, the kidneys on the backside of your body, surrounded with adipose tissue, with fat, to make sure that they don't take too much trauma if you accidentally get hit from behind. Triglycerides are made of two main components. Component number one is the glycerol backbone. So this is a chemical molecule called glycerol. And when we talk about triglycerides, glycerol is going to have three little fatty acid chains attached to it. Now, fatty acid chains, like we see here, 1, 2, and 3, or like we see here, 1, 2, and 3, these fatty acid tails come in two different varieties. Saturated fatty acids are the fatty acid tails that don't have any double bonds in them. So notice how this fatty acid is straight. It lays flat. This is the kind of fatty acid that we find inside animal fats. So human fats, beef, pork, the kind of lipid that's inside there, triglyceride inside there, is built with these saturated fatty acid tails. When we talk about plant fatty acid tails, they use what's called unsaturated fatty acids. Notice with unsaturated fatty acids, we have this double bond which leads these molecules to not lay as flat or not lay as straight. So lipids, my long-term energy storage in the body. Triglycerides in particular have three fatty acid tails and a glycerol backbone. These store that energy really efficiently. We also have many lipids in the body that are called phospholipids. When we talk about phospholipids, these have those fatty acid tails, making it a lipid, but they also have a phosphate group, hence the phospho name. Phospholipids that are the major component of our plasma membrane. So when we look at the structure of a phospholipid, we've got a phosphate group, which is polar. Remember that hydrophilic things are polar things. They like to be around water because water is polar as well. We also see, though, those lipid tails that we saw on the triglycerides. Phospholipids only have two of them, but regardless, those lipid tails are nonpolar. Nonpolar meaning hydrophobic, meaning do not put me by water, I do not like it. So what this means with a phospholipid is it has one part of it, the phosphate group up here, we actually call this the head group, that loves water, and we have the tails that are hydrophobic, they hate water. There's a fancy word that I'm not going to ask you about, but it's called amphipathic. Amphipathic is kind of like an amphibian, where they like land sometimes, they like water other times. That's the thing like we see here with a phospholipid. It likes water sometimes, it hates water other times, depending on the part that we're looking at. This is why your plasma membrane has what's called a bilayer structure. So if you notice over here, we've got our head group that's polar, and we've got our tails that are nonpolar. When I put them together in this arrangement with the heads on the outside and the heads on the very inside of the membrane, all of those tails are stuck here together in the middle. By being together here in the middle, this is going to allow us to keep water out of our plasma membrane so that these tails, who don't like water, never have to bump into it, while the head groups on the very outside or the very inside, groups that do like water, will be in touch with the water that's inside the cell, called cytosol, or the water that's outside the cell, interstitial fluid. So, why is this bilayer structure good? This bilayer structure keeps both parts of a phospholipid happy. It keeps the part that likes water by water, and the part that doesn't like water away from water. One last kind of lipid to mention for you, and these are what are called steroids. When we talk about steroids, these are things that don't have that straight line structure that we saw before, but they have these 4 rings inside of them. So just like we saw before, carbon, hydrogen, oxygen, but not in a line, in these ring structures. The only thing that makes these hydrocarbon rings different from one another is what they have attached at various parts of them. So it's actually what we call the side chain that determines the functions of each of these steroids. 100%, I promise you, I will not give you a picture like this and ask you which steroid you're looking at. I promise I won't do that. But if you see any structure with these 4 hydrocarbon rings, know that we're looking at a lipid that is a steroid. All of these steroids are formed from the same precursor molecule. We always start with cholesterol. So cholesterol with its 4 carbon rings gets modified into each of these structures that we see around here, each of my steroids. Steroids do different things in the body. One of them that we'll talk about just briefly is the fact that they're used to form the plasma membrane, or to stabilize the plasma membrane. So when I have saturated fatty acids, notice that they fit together really nicely. But not all of my phospholipids are saturated. Some of them are unsaturated. And when they're unsaturated, this leads there to be some space in between those phospholipids. This membrane is not particularly stable. That's where cholesterol comes in and wedges in between those fatty acid tails, helping to stabilize the membrane, or helping it so that these unsaturated fatty acids don't move too far away from one another. The other thing, though, that steroids do, that you'll cover in depth in AMP2, is they are our steroid hormones. So things that we see up here like estrogen or testosterone, also cortisol, the stress hormone. All of these different steroid hormones have different effects in the body, and that comes down to this 4-ring structure that we see with all of these different side chains that come off of that. So lipids, my carbon, hydrogen, oxygen molecule in the body that help me with energy storage, that help form my plasma membrane, and that act as hormones or stabilizers for the membrane.